Have you ever gazed at a clear, cloudless night sky? You could be awestruck how wonderful and intriguing it is. On a clear night sky, you can spend hours looking at the stars and wondering how they form such inspiring patterns and configurations. Ancient sky watchers looked at configuration of stars and identified them with familiar patterns or mythological figures. Joining the positions of the bright stars in these configurations gave rise to what we now call constellations. You can actually see how the positions of bright stars are joined together to form these regions in the sky, which we call constellations, like Gemini, Taurus, Aries, and so on. Some ancient drawings and artworks depict some of these familiar shapes. Now look at this cup from ancient Greece. This cup, dated back to 600 BC, was found in Greece. The drawings are identified as constellations. The tail end of a bull is the Taurus. If you look here, you can see that. A snake is the Hydra. A hare is Lepus. A dog is Canis Major, and so on. Look at the constellation Orion. Orion the Hunter. Betelgeuse, Bellatrix, Alnitak, Saiph, Rigel, and Mintaka are the brightest stars in this constellation. Joining their positions, look at how they actually give out the picture of Orion the Hunter. Now, here you can see Orion constellation. Can you picture it here? If you look here, the stretched arms of Orion with the shield. And if you look closely, you can actually see his faithful dog out here. That's the Canis Major constellation. And of course he's a hunter, and here's the rabbit that he just killed. And now look at the imagination of ancient people. Now most of the constellations, most of the 88 constellations visible to us throughout the year, most of the names are actually derived from mythology. Andromeda, Perseus, and Hercules are well-known examples. Now, here are the 88 constellations and their names. I don't think you need to remember them. Let me recount to you the story of Andromeda and Perseus. Well, these are actually Greek mythology stories, and if you have read some of them, you probably will remember what I'm talking about. Now, constellation Andromeda is visible in both the northern and southern hemisphere. Now, what is the story behind Andromeda? If you look, Andromeda is right here, and Perseus is right here. Cassiopeia, we will be talking about these. Pegasus, these are the group of constellations we will be talking about. Now, Princess Andromeda is a character from Greek mythology. She was famed for her beauty and would eventually marry the hero Perseus. Andromeda's mother was Queen Cassiopeia. She was also known famously for her beauty, but infamously for her vanity. Her vainness would eventually upset the gods, and a sea monster was dispatched to destroy her kingdom. The queen and her husband, King Cepheus, thought the best thing to do would be to chain their daughter Andromeda to a rock as an offering to the sea monster. What a terrible thing to do by parents. Luckily, Perseus, son of mighty Zeus, was there to save the day. He freed her and her chains and killed the monster. Well, the pair married and shortly after settled in Perseus's home island. During their marriage, they had a total of 9 children. After her death, Andromeda was placed in the heavens alongside her husband Perseus and mother Cassiopeia. Andromeda's image appears upside down. Well, something like this. Now, Andromeda is part of the Perseus group of constellations, which also include Cassiopeia and Perseus, as I just showed you. The Andromeda, the Perseus constellation, the Cassiopeia constellation, and the Pegasus. They all form a group called the Perseus group. Now, that is the mythological story about the constellation Andromeda. Now, here is the story, the mythological story about Perseus constellation. Medusa, I'm sure most of you have heard about Medusa. Medusa was originally a golden-haired fair maiden who, as a priestess of Athena, was devoted to a life of celibacy. However, after being wooed by Poseidon and falling for him, she forgot her vows and married him. For this offense, she was punished by the goddess in a most terrible manner. Each wavy lock of the beautiful hair that had charmed her husband was changed into venomous snake. Her once gentle, love-inspiring eyes turned into bloodshot, while her former hue and milk-white skin assumed a loathsome greenish tinge. She fled home, never to return, wandering about, abhorred, dreaded, and shunned by the rest of the world, and turned into a character worthy of her outer appearance. In her despair, she fled to Africa, where, while wandering restlessly from place to place, young snakes dropped from her hair, and that is how, according to the ancient Greeks, Africa became a hotbed of venomous reptiles. Do you believe that? I lived in Africa, and I didn't see many of them. She turned into stone whomever she gazed upon, till at last, after a life of nameless misery, deliverance came to her in the shape of death, and at the hands of Perseus. Now, look at that. Perseus is decapitating Medusa. Now, he has to be careful because he cannot look into her face, because if she gazes at him, he will turn into stone. And look at the comparison between this mythological picture and the constellation Perseus. Now, here you can actually see Perseus decapitating. Perseus is the 24th largest constellation, and here you can see that. And the brightest star in Perseus is called Myrfak. The astronomical name of Myrfak is Alpha Persei. We will talk about the way stars are named later on. Alpha Persei has 7.3 solar masses. It's a very massive star and about 60 times the size of our Sun and 5,000 times more luminous. Alright, let's now discuss briefly how we can measure distances between faraway objects in the sky. Our conventional methods of measuring distances between two objects on Earth make very little sense when measuring vast distances between celestial objects. Because of this, astronomers measure the distance between celestial objects based on the angle they make with an observational point on the Earth. Known as angular distances or angular separation, distances are expressed in terms of degrees, arc minutes, and arc seconds. 1 degree contains 60 arc minutes, and each arc minute contains 60 arc seconds. I'm sure all of you know how to measure degrees. Now, what is the meaning of angular distance? Now, look at these pictures. If you will stretch your arm and just point one finger, and if you have two distant objects like the star, one on either side, then the angular separation between those two stars is 1 degree. On the other hand, if you stretch out those 3 fingers, the angular separation is 5 degrees. And if you have the closed fist right in front of you, you got to have a stretched arm and then have the closed fist so that the objects appear on each side of it. Now here, if this is one star and this is the other star, the angular separation between them is 10 degrees. The angular separation between these two stars is approximately 10 degrees. And now, look what this is. That gives you 15 degrees. And 25 degrees is your thumb and your small finger, and the others closed. You get an angular separation of 25 degrees. In fact, have you ever seen this constellation? This is a very prominent constellation in the night sky. This is the Big Dipper. That is across about 25 degrees. We will now discuss the most important concept of celestial sphere and learn how to locate celestial objects. Now, on Earth, how do we locate a position on the surface of the Earth? We use longitude and latitude, don't we? Now, seen from the Earth, if you notice, this is our Earth. Now, if you are standing on the surface of the Earth, the night sky looks like a huge dome with stars stuck on it inside, isn't it? If the Earth beneath just vanished, if the Earth simply vanishes, we would see stars all around us, and we would have the breathtaking sensation of hanging at the center of an immense star-speckled sphere. Have you ever imagined about that? Wouldn't that be wonderful? Astronomers designate the positions of stars by where they are on the celestial sphere. In other words, if you want to locate the position of the star, we've got to develop a skill for doing that. Now, all stars, when you look up, all stars appears to be on the celestial sphere. But are they all the same distance from the Earth? No, they are not. They are at different distances. Now, in order to locate the position, first of all, we've got to define a term called celestial equator. Now, what is celestial equator? Now, you know what the Earth's equator is. Well, the Earth is inside there, and that is Earth's equator. And if you project it onto the celestial sphere, look at that. That is the celestial equator. So, at any point, if you stand at the Earth's equator and look up, you're actually looking at the celestial equator. It's directly above. All right. So celestial equator is a line on the celestial sphere directly above the Earth's equator. Like the equator on the Earth, the celestial equator lies halfway between two poles. If you notice, on the Earth we have a North Pole and a South Pole. Similarly, on the celestial sphere we have a North celestial pole and a South celestial pole. Now, we see the Sun moving around the Earth, and we see the Sun on the celestial sphere, don't we? How about the path taken by the Sun? Well, remember, the Sun really do not move along a path. It is the rotation of the Earth that makes as though the Sun is going around the Earth. It actually doesn't do that. So, we are talking about the apparent path of the Sun. The Sun rises in the east and sets in the west, and it continues. Now, if you trace its path, how will it look like? The ecliptic is the apparent path of the Sun on the celestial sphere. It's apparent because it is not real. Now, how does it look like? Now, here is another drawing of the celestial sphere. Now, I have eliminated Earth from the center, but the blue circle is the apparent path of the Sun around the Earth. Now, this is called the ecliptic. The ecliptic. Now, if you notice, the ecliptic is not aligned with the celestial equator. They make an angle. Now, how much is that angle? The angle is 23.5 degrees. Now, if you notice, there are 2 points where the ecliptic crosses the celestial equator. Now, this one I am pointing is called the autumnal equinox. So, the Sun will cross the celestial equator at the autumnal equinox. It moves and goes towards the south and reaches the south end at the winter solstice, then moves towards the vernal equinox. Now, this is March 21st. Then it goes towards the north, the summer solstice, and back at the autumnal equinox, and so on. So the ecliptic is inclined 23.5 degrees with the celestial equator. Half the ecliptic is above the celestial equator, is that right? That half is above the celestial equator, and the other half is below the celestial equator. Now, what are equinoxes? Equinoxes are points on the celestial sphere where the ecliptic, that is the apparent path of the Sun around the Earth, crosses the celestial equator. It crosses the celestial equator on March 21st, called the vernal equinox. That's the vernal equinox. Then goes farthest north at the summer solstice. That is the farthest north the Sun will go. then crosses the celestial equator at the vernal equinox, that is on September 21st. When does the summer solstice occur? That is June 21st. And it crosses the celestial equator again at autumnal equinox on September 21st. Then it moves to south, and here we have the winter solstice, that is December 21st. Now the summer solstice occurs when the ecliptic is 23.5 degrees north of the celestial equator. So that angle is 23.5 degrees. Similarly, the winter solstice occurs when the ecliptic is 23.5 degrees south of the celestial equator. So in place of the longitude and latitude to determine the position on the surface of the Earth, we use two other terms to determine the position of a celestial object, and they are declination and right ascension. Declination and right ascension. Now let's define each of these terms. Now, what is declination? Now, imagine a great circle. We want to find the declination of this star. So what you need to do is draw a big circle. Look at that big circle. That big circle goes through celestial North Pole, through the object that we want to determine the position, that is the star, then the celestial South Pole, and that is the big circle. And look at the big circle cuts the celestial equator at this point. And that point actually is called the foot. Now, the angle that this arc makes is actually the declination. So the declination is sort of gives you the altitude of the star. So what is the declination? The declination is measured from the foot. What is the foot? The foot is the point where the great circle that goes through the object, the north celestial pole, the south celestial pole. Now, where the great circle cuts the celestial equator, that is the foot. The angle measured from the foot to the object, that is declination. All right. So once you know how to find declination, now we also need to locate the point using another coordinate. Now that is called the right ascension. Now, the right ascension is analogous to longitude. Now, if you remember, or if you know, the beginning point for measuring longitude is arbitrary. In the same way, the measuring of the right ascension, where do you start, is arbitrary. But astronomers have actually chosen that arbitrary point to be the vernal equinox. Now, declination is measured in degrees, arc minutes, and arc seconds. But right ascension is not measured in degrees. It is measured in hours, minutes, and seconds. Why? Because the Earth takes 24 hours to complete one rotation. So the position is actually measured in hours. Now, 1 hour, 2 hour, 3 hour, 4 hour, when you complete the circle, it will be 24 hours. The complete circle is 24 hours. So the number of hours measured from the vernal equinox to the foot, you know what a foot is now, the number of hours in this length is called the right ascension. So declination is expressed in degrees, arc minutes, and arc seconds. Now, positive declination, positive angles are measured to the north of the celestial equator, and negative angles are measured to the south of the celestial equator. Right ascension is measured in hours, minutes, and seconds from 0 to 24 hours. Now, astronomers set up this arrangement long ago because the Earth completes one turn in 24 hours. So the celestial sphere appears to take 24 hours to complete one rotation, one complete turn around the Earth. Now let's answer the question, why do stars rise and set? Have you ever answered that question? Why do stars rise and set? Well, if you look at this star, after some time it's going to be over here and it's going to go around a circle, right? If you have a star here, it rises, it comes to the zenith. What is zenith? That is a point directly overhead. Then it sets, well, it goes around and then rises again. Is that right? Well, that's an illusion caused by the rotation of the Earth. Every object on the celestial sphere appears to make a simple daily circle around the Earth. So a star here makes that circle. A star here will make that circle. How about a star near the North Pole? Look at that. Its circle is very small. That means a star at the North Pole may not even make any circle. So stars near the North Celestial Pole are circumpolar, means they just describe circles around the pole, around the North Pole and around the South Pole. Now, stars near the South Celestial Pole never rises above the horizon. That means if you are in the north, you will not even see the stars, the circumpolar star in the south, because they never rises above the horizon. All other stars have daily circles. So stars in this region, you can see they rise and set, and stars in the North Celestial Pole are circumpolar, but stars near the South Celestial Pole you cannot see. And you can extend the same argument to people observing from the south, namely if you live in Australia. Now, are the stars really moving? It is an illusion created by the west to east rotation of the Earth. The Earth rotates from west to east, and that's why we see things rising at the east and setting at the west. Now, we talked about constellations. Can all of us at different points on the Earth see all the constellations? Well, the constellations we can see depend on our latitude. Now, if you are on the same latitude but different longitude, you will see the same constellations, but a little later, and so on. So constellations you see depend on your latitude and not on your longitude. In other words, people at the same longitude, people at the same latitude but different longitude will see the same set of constellations. Now, latitude affects the constellations we see because it affects the locations of the horizon and zenith relative to the celestial sphere. I hope that is not a difficult concept to understand. If you are located, this is the Earth, the circle you see is the Earth. If you are located here, in that latitude, all the constellations in this region will be visible to you. But if you are on a different latitude, the constellations will be different. But it doesn't change with the longitude. All right? Now, constellations visible at a particular time at night changes as we orbit the sun, isn't it? The night sky changes throughout the year because the Earth is changing position in its orbit around the sun. In other words, in 1 month if you see the sun in a particular constellation, let's look at this picture. Now, if the sun in March, for example, you see the sun in the constellation Virgo. But if you move to April, May, June, the sun will move from Virgo to Libra to Scorpio to Sagittarius and Capricorn and so on. So, over the course of the year, the sun appears to be in front of or in different constellations. 1 month the sun appears to be in Gemini, say over here maybe. The next month it is in Cancer. And then over to Leo, Virgo, and so on. Now, the next question we try to answer is, but this is again another illustration showing how the position of the sun changes from constellation to constellation. All right? In other words, that's the Earth, that is the sun, and as the Earth rotates, as the Earth revolves around the sun, you see the sun in different constellations at different times of the year. All right. Let's now talk about seasons. Now, very often people think that we got summer and winter because at sometimes the Earth is closer to the sun and sometimes a little farther away. No, that is not the reason for the season. Over the course of the year, the angle of tilt, you know that the Earth's axis is tilted to the vertical by that 23.5 degrees. Now, as the Earth revolves around the sun, that tilt doesn't change. But what changes is the orientation of the Earth's tilt with respect to the sun. Now, because it changes, at a certain time, the northern hemisphere is oriented towards the sun for half the year, and away from the sun the other half. Now, if you look here, as the Earth rotates around the sun, let's look at the first half. During the first half, the sun's light is falling directly at the actually it is falling directly at the Tropic of Cancer, that is 23.5 degrees north of the equator, and most of the northern regions therefore receive more light than the southern regions. So we got summer in the north and winter in the south, and as it changes you can see as the Earth comes here, that is when the sun's rays will fall directly at the equator. And as it continues, what happens? The orientation changes so that the light from the sun is falling directly at the Tropic of Capricorn, 23.5 degrees south of the equator. And that is the time when the southern hemisphere receives much more light and heat than the northern hemisphere. So summer in the south, winter at the north. So this is the reason why we got seasons on the surface of the Earth, not because of the closeness. If you notice, the Earth's orbit is like an ellipse. Sometimes the Earth is farther away, and sometimes it is closer. But the seasons are not due to that. All right? All right, let's now move on and talk about our moon. Now that we talked about the seasons on the Earth, let's look at our Earth's companion, the moon. As the moon orbits around the Earth once per month, the angle between the Earth, the moon, and the sun changes, and we see this as the cycle of the moon's phases. Now, the moon rotates on its axis, you know, that just like the Earth, the moon also rotates and also revolves around the Earth. Now, the time taken for one rotation and the time taken for one revolution is exactly the same. And therefore, what's the results because of that? And therefore, half the moon is always hidden from us. We only see one half of the moon. The reason is the period of rotation and the period of revolution of the sun are exactly the same. Now, like the Earth, the moon is a sphere which is always illuminated by the sun. But as the moon orbits the Earth, we get to see more or less of the illuminated half. Now, during each lunar orbit, we see moon's appearance change from not visibly illuminated through partially illuminated to fully illuminated, then back partially illuminated to not illuminated again. Now, there are 8 distinct stages of this that I just talked about. That not illuminated gives way to partially illuminated, gives way to fully illuminated, gives way to partially illuminated, and so on. Now, let's take a look at these 8 distinct stages on the moon's face. What is the first stage we start with? What do you call this? This is the new moon phase. The moon's unilluminated side is facing the Earth. The illuminated side is away from us. What is the next stage? The moon appears to be partly but less than half illuminated by direct sun. The fraction of the moon's disk that is illuminated is decreasing. No, is it decreasing? No, it's increasing. Here there is no illumination. The illumination increases, and this is the waxing crescent. So the waxing crescent, the fraction of the illuminated part is increasing, not decreasing, as I said earlier. How about this? This is called the first quarter. One half the moon appears to be illuminated by direct sunlight. And again, the fraction of the moon's disk that is illuminated is it increasing or decreasing? Is increasing. And that leads us to waxing gibbous. Now, the moon appears to be more than 1/2 fully illuminated, and the fraction of the moon's disk that is illuminated is increasing, leading us to the full moon, right? That moon's fully illuminated side is now facing the Earth, and the moon appears to be completely illuminated, and that is a wonderful sight from the surface of the Earth. Okay, what is the next phase? Now the illuminated part is decreasing, isn't it? In the waning gibbous stage, the moon appears to be more than 1/2 illuminated by direct sunlight from the sun, but the illuminated part is now decreasing. And that leads us to the last quarter. 1/2 of the moon appears to be illuminated. And again, is the illuminated part increasing or decreasing? It is decreasing. There you go. And finally, you come to the 8th stage, and what do you call it? The waning crescent. The moon appears to be partly but less than 1/2 illuminated. The fraction of the moon's disk that is illuminated is decreasing, will give way to what? So the new moon and the cycle will continue. Alright, now that is the description of our moon and how the phases occur. But the moon also causes some other phenomenon, the solar eclipse. The moon passing between the sun and the earth, now that's the orbit of the moon. Now sometimes the shadow of the moon might reach the earth. So the moon passing between the sun and the earth can sometimes block the sun and prevent the light from reaching the sun. When this happens, a shadow of the moon falls on the earth. And we say that the sun has been eclipsed by the moon. Now, this does not happen every month because moon's orbit around the earth is slightly tilted about 5 degrees to the earth's orbit. And so, actually, most of the time, the earth will miss the shadow. But at least twice a year, some part of the moon's shadow will fall on the earth, and we will experience a solar eclipse, that is, eclipsing of the sun, covering the sun. Is that right? Okay. Now, the shadow is actually made up of 2 parts. There is a real dark shadow and about a half shadow. The darker shadow is called the umbra, and the other part is called the penumbra. All right? Now, look at the sequence of events. This is actually the sequence of events that gave rise to a total solar eclipse in 1999. Very interesting to watch. All right. Well, if an eclipse occurs while the moon is on the far side of the orbit, remember the moon's orbit is not also circular. Sometimes it is closer to the earth, sometimes it is farther. When it is closer to the earth, you get the mega moon. Is that right? You have seen that a couple of times at least. One occurred about a couple of weeks ago. Now, when the moon is in its farther from the Earth, the shadow may not reach the Earth. That means you will not see the complete shadow. The moon appears smaller than the sun, but it can't completely cover it. Now, when that happens, we say it is an annular eclipse. Now, if you are within this path, you can see only at certain regions on the Earth you can view this kind of eclipse. You actually see a ring or an annulus of bright sunlight surrounding the moon. And I have a picture of that here, I think. Now here, this is the picture of an annular eclipse. All right. Look at that annulus that we just talked about. Well, what we talked about so far is solar eclipse, how the moon eclipses the sun. In the same way, you can have lunar eclipse. The moon can be eclipsed by what? By the Earth, actually. Because when the Earth comes in between the moon and the sun, the Earth's shadow will fall on the moon. And when it happens, we have a lunar eclipse. Here again, you can have two different kinds of shadow. That's a complete shadow, that's the umbra, and the penumbra. So when the moon goes around the Earth, it goes from a penumbral region to an umbral region, that is total eclipse, to a penumbral region and out. All right, I have a picture of that. It comes on to a penumbral region, to an umbral region, to a penumbral region, and so on. Well, we actually went through briefly describing the night sky, how we can locate positions of an object in the night sky, how the moon go through the various phases, and so on. We will continue with more of the night sky sometime later on. All right?